Ah, okay, good. So I don't know how to do that. That's too bad here. Okay. Hope it's going to let me do this. No, it's not going to let me do that. I'm going to have to close that off when I get ready to do it. Yeah, in fact, maybe because I don't know how to do this, I'm going to close this. No. So how do I get it to stop doing that? I don't know how to turn that off. It should turn that off. That's really kind of annoying. So it'll let me do that, but then when I get to this window here, it wants me to draw in the window. I don't understand that. Maybe I can just do this. Ah, good. Let's stop this. Okay, so get a little bit further in. Thoughts about how it works? Yeah, it's not. That's one guess, right? Okay, what's your other guess? In the E&M course, you eliminated the magnetism. So it's a capacitance. He's changing the capacitance of the pickup by moving his hand closer and farther. And the circuit is built to have us detect small change in capacitance and okay, that's pretty good. So it's a capacitance meter. Okay, and I can't even get this doggone thing to open up. How do we do this here? Here we go. Okay. So anybody know what that instrument is called? Yeah, it's a theremin. Do you know about the history of the theremin? It's an interesting Cold War thing going on because it was a Russian named Theremin who invented this instrument, and he became very popular, toured all over the United States during the height of the Cold War. It turned out he was also spying on all kinds of facilities and using his tour of the United States to go check out the military installations and things like that. Okay, so he got sent home. But the theremin still sticks around. They made a bunch of these things back in those days. I think the story is correct. It's a pretty interesting device. Okay, so now let's go back to discussion of, we've got all kinds of fields floating around, forces and potential energies and electric fields and electrostatic potential. God bless. How do we keep track of all these things? Okay, what is the difference between them? So let's start with a charge. This generates an electric field in the plana. And if we put a test charge, so I'm going to distinguish these charges by uppercase and lowercase. Then there are forces that exist. Of course, if they're both of the same type, it's a repulsive force. And the magnitude of the repulsive force is goes inversely like the square of the distance between them and proportional to the charges, right? And then there's an electrostatic potential. Oops, it's Q here. Electrostatic potential energy. I said it wrong. It's a potential energy, which is the product of the two charges divided by the distance. If the charges are the same, then this is uphill from infinity. It means it has a higher potential energy than if the charges are infinitely separated. If the charges are opposite, then the force is attractive and the potential energy is negative compared to infinity. It's downhill from infinity. Okay. Now, but we said that this charge, Q, generates an electric field in the plana. We don't even need the test charge. The test charge can give us evidence of the electric field that's present. But the electric field exists even without the test charge. It's in the plana, at all locations in the plana. So if we come over at a distance r here, there's no charge here. I don't want to put a test charge there. I just want to know what is the electric field at this place. And the electric field then is proportional to the charge at the big Q. But there's no test charge, so there's only one charge involved in the electric field. It's not a product of two charges, it's only one. And the electrostatic potential is big Q over R. Okay, again, just one charge. So the force will be the test charge times the electric field. That would be the force present on the test charge if I put the test charge there. The electric field exists there regardless of whether there's a test charge. But if I put the test charge in, there's a force on it that's proportional to the electric field. And the potential energy is Q times phi. Again, the electrostatic potential exists whether or not I have the test charge in there. So even if there's no test charge, there's an electrostatic potential at that location in the plana. The electrostatic potential, also called the scalar potential, phi, is a further specification of the electric field. Or you can think of it this way also, because the potential energy is proportional to the test charge, you could say it's the potential energy divided by the test charge, right? It's the potential energy that a test charge would have divided by the charge on that test charge. Okay, so this is the relationship between the electric field and the force and the electrostatic potential and the potential energy. And it's a little bit unfortunate that we have these two words that are so closely related to each other, the potential energy and the electrostatic potential. But the electrostatic potential is not a potential energy. You could think of it as a potential energy per charge if you were to put something in there, right? But it exists even without the test charge. So the terminology is it's potentially confusing, right? Because we have all these potentials floating around. So just try to sort that out in your head. Does that help with the relationship between electrostatic potential? Now we also had, for a conservative force, we have that the force is the negative gradient of the potential energy, and in the same way we have that the electric field is the negative gradient of the electrostatic potential. So if we multiply the bottom equation by the charge, the test charge, we get the top equation, right? Okay, so these are closely related in that sense. The electric field and the electrostatic potential tell us something about the state of the plana. Whether or not we've got the test charge in there. So you can think of it as being telling about the state of the plana without the test charge present. Okay. Now there was another item to talk about here, and that was, we've talked about two different kinds of current. Come on, there we go. Two different kinds of current, I now and J. And they're related to each other. J is a current density. And when we say current here, what we mean is charge current density. So it's Q times divided by a volume times a speed. So it's a Q per area per time. It's a charge, it's the amount of charge that would pass per unit area per unit time. And so if we have a wire, for example, that has some radius, and if the current were distributed, could be distributed uniformly over that wire, over this current doesn't actually do that often, but let's suppose that we could distribute the current uniformly over the wire. So J would be, well, it is present, the density there. If we multiply by the area, then that is the total current flowing in the wire. So the total current then, the dimensionality of, this is the dimensionality of J, the dimensionality of I, so this is JA, the dimensionality of I is just a current, is a charge per unit time. And that's the difference between the two. So we talk, when we come to discuss Ohm's law, Ohm's law is expressed in two different ways. One is the relationship for the total current in the wire, the other one is the relationship for the J in the material. Okay, now when we were looking at the electroscope, you remember, so let me draw a picture of the electroscope. Then I brought in a demonstration here. It had two little, well, this is an electroscope. It wasn't exactly the version that I used in class, but anyway, this is the version that's discussed in the text. There's a piece of metal with two little metal leaves at the bottom, and we charged up a wire by rubbing it and getting charged up a rod by rubbing it and then bringing the rod, and I could touch this electroscope and it would charge the electroscope, and you could see that in the charged condition these leaves fly apart like that. There's charges now distributed, all suppose they're positive charges, it doesn't matter, they're all the same kind, and the parts that can move away from each other are going to move away because they repel each other. The charge is distributed, it's very mobile on there, so, but anyway, it can't get away from itself entirely, so it spreads it apart like that. Okay, but I could also, if you remember, let's suppose that the electroscope starts off in the condition on the left-hand side where it's not charged. I could also bring the rod up without touching it. Do you remember this? I could bring it close and the leaves would open up. But then if I take the rod away, the leaves go back. So I could cause something to happen in the electroscope just by bringing a charged rod close, not touching it. I didn't actually charge the electroscope because if I take the rod away, it goes back to normal. So what's happening in that case, if I bring up a rod here that's charged, and I have a bunch of charge on this rod creates an electric field. And the charges in the metal are mobile. So they're going to, the positive charge is going to move away from this rod, or we could say the negative charges accumulate. So I get charges building up, and then the leaves push apart because I've got positive charge induced on them and negative charges up at the top. So this is now the whole thing is neutral. It hasn't gained net charge, but it's rearranged the charges. And that's called electrostatic or electric induction. Electric or electrostatic. I've pushed the charges around. The pieces, the parts of the substance there have been rearranged by the presence of the electric field. I could do this, for example, if I had a block of metal, a big piece of metal, and I bring a charge here, call it plus. The charges are mobile, and so I'll get negative charges on this end and positive charges distributed around the outside like this. Okay. Now, if this is a big cube of metal, so remember this charge that I'm bringing up, the one on the left there, is creating an electric field, and then the charges in the metal are moving in response to that electric field. So I have a combination of two electric fields. There's the electric field because of the charge that I'm bringing up from the left, and there's another electric field, which is the electric field from the charges in the metal that have been rearranged. And those two electric fields cancel out perfectly. How do you know that? Well, the idea is that we've said that the electric field inside of a conductor is going to become 0, because if it's not 0, it's going to start moving charges around. So the charges are going to keep moving around until they cancel out whatever electric field is present. So these charges that are induced in the metal are arranging themselves so as to perfectly cancel the electric field that's present because of that body that I brought up to the metal outside. And in fact, you can get kind of fancy with this. It's kind of interesting how you can do this. You could make this metal hollow. So let's do this. And now we bring up a charge, and in fact, I get the same induced charge here around the outside. What is the electric field inside of that hollow piece of metal? It's 0. The electric field is 0 inside. It's screened out by being inside of the conductor. And this is the basis of a Faraday cage. We used to have one down in the basement of Kynard. I don't think it's there anymore. It was smaller than this room, but it was big enough to go inside, set up an experiment inside, had some equipment inside. And the purpose of the cage was just a wire mesh, and the purpose of the cage was to screen out stray external electric fields. You want to control what's inside. So any electric fields you generate inside have to be generated from inside. Nothing outside is going to generate the electric field. At least that's the idea of the screen. So by having two different types of charge like this, you can have screening going on. Gravity doesn't do this because it's only there's only an attractive interaction in a gravitational field. Because we have both attractive and repulsive interactions going on, we can have this screening. So screening is something that's new. Having those two different types of charges that can repel like charges or attract opposite charges. Okay. So now the same thing happens here. Let's remember we were talking about the having this circuit here with a battery hooked up to it. I'm going to for the moment leave out the resistor that I had in there. Let's just hook up a capacitor to a battery, and the capacitor is just parallel plates. And if current is flowing in here, that's going to end up charging the capacitor. And in fact, the current is the rate at which the charge is building up, right? Current is a charge per time. And so the presence of current flowing into the top plate is going to charge that plate positive, like this. Okay, now that positive charge is going to induce a rearrangement of charges in the bottom plate. The bottom plate is going to charge negative in response, and current will flow then this way, right? So it's as though current is flowing through the capacitor, even though there's a gap. And there is no charge flowing across the plates. It's not discharging directly across the plate. In other words, there's not charge being transferred from the top plate to the bottom plate. And nonetheless, because of this electrostatic induction, charging the top plate oppositely charges the bottom plate, because the capacitor is connected to the battery. And so you have the current then flows out of the battery and charges the capacitor like this. Pretty neat. Okay, so now let's look at that capacitor plate. Let's look at the field that's present in the capacitor. Remember, we said that if we're considering, and this is the situation we want to consider. We want to consider two parallel plates separated by a distance d. And let's consider them to be square or maybe circuit, or anyway, the radius or the length of in this direction is much larger than d. Now, in that case, we can look at the electric field in here. I'm going to put positive charges, and I'm going to distribute them, and I'm going to assume that they're distributed uniformly. Okay, and again, that may or may not happen. You have to be careful about these assumptions, because the charges are free to rearrange themselves to try to get away from each other, because they're all opposite charges. So, but let's just suppose for the moment that we could put the charges uniformly on this plate, top and bottom. We have a plus Q on the top, a minus Q on the bottom. Okay, now because we've gone through this argument using Gauss's law that the electric field in this region should be uniform between the plates, E field here. And that's pretty good as long as you're close to the center and you're not close to the edges. So this argument that this calculation I'm about to do is just going to depend on this extreme case where the gap is really small compared to the dimension of the plate. Okay. So now, and we calculated that, the electric field now, remember, is 4 pi sigma. The strength of the electric field there is pointing in the direction that I've shown there, 4 pi sigma, where sigma is the charge per unit area if we just could distribute it uniformly over that plate. Okay. Now the electric field is uniform in that region. Let's suppose we just take it uniform and not worry about the edge effects. Let's just say over that, most of that area it's uniform and has the same magnitude and so forth. Let's make that assumption. What does phi look like? The electrostatic potential, the negative gradient of the electrostatic potential is the E field. We said the E field is uniform. It's constant everywhere in there. So what does that mean about phi?
It's dependent the distance from the plate.
In what way?
Just directly proportional.
Directly proportional. It's a linear dependence on this distance. So we would say if this is the z direction, the electrostatic potential is some constant minus Ez, where E is that constant uniform electric field, right? So from this we take the negative gradient of phi, we get E is equal to E, right? E is this E here. Okay, so it varies linearly across the gap, and the difference in the electrostatic potential between the top and the bottom plates is then negative E d, right? Where d is the separation between the plates. So let's call that that phi is the potential difference. Yeah, so let's call it that potential difference. And and let's write this in terms of the charge, minus 4 pi q over a d. And the proportionality here, the way that it's typically defined, then it's the negative. So we say that the potential drop, actually it's the other way around, excuse me, sorry. The charge divided by the potential drop, we usually put a negative sign here, is called capacitance. And you can see the capacitance here depends upon, let's see, it's A over 4 pi d. Capacitance depends on the geometry. How did you arrange these plates? You could have different kinds of capacitors. You could have a couple of cylinders, concentric cylinders, put a positive charge on one, put a negative charge on the other. The electric field is not uniform here. Remember, it goes like 1 over distance, but you could still figure out the potential difference between the inner and the outer plates. So there's still always a proportionality between the charge that you can put on the capacitor and the potential difference between the parts of the capacitor, the parallel plates. So, and they're just directly proportional to each other in this analysis. You put on more potential difference, you're going to get more charge build up, or the other way around, put more charge on, you get a bigger potential difference. So, and you can also play with this by putting stuff in between the plates. We had the two plates here. You could fill it up with other material, and that would alter the capacitance as well. You don't want to fill it up with a conductor because that would short the capacitor. You want to fill it up with some kind of insulating material. So you fill it up with an insulator. Water is not a good insulator, right? So you need to fill it up with something that insulates, doesn't polarize much, and that would then allow increased capacitance. So capacitors are made like that. Okay, so now let's go back to the circuit that we were considering. We were looking at the RC circuit here. We had a circuit. Now let's put the battery back, the battery and the resistor. The symbol for the resistor is that wiggly line like that. Capacitor is, even if it's not a parallel plate, is diagrammed to be a parallel plate like that. So we have a resistor, a capacitor, and so now it's common to talk about the voltage of the battery, or that could be also the electrostatic generator, you know, the Vandergrift thing, the thing with a crank that I turned to charge up the plates before. So but the common one that you can get is a battery that's just electrochemical battery. And the reason for that potential difference there has to do with the nature of the metals, two different kinds of metals that you put close together with some kind of solution between them. Anyway, so we won't talk about the battery. We'll just consider it as a source of potential difference. But unfortunately, right, here's to add to the confusion. We usually use the symbol V for potential energy, but people also use V to represent an electrostatic potential difference, which, you know, phi is what we've been using, but some people will use V naught to be the voltage, right? Voltage is potential, electrostatic potential. Potential energy, you see these problems here we've got? You have to kind of sort this out in your mind. The terminology is not ideal. So I put a voltage on here, and the voltage is an electrostatic potential difference. It's not a potential energy. It's a potential energy per charge, even though I'm going to use the sign V, the symbol V for it. Okay, so I put the voltage on there. Now initially, let's suppose we start off, in fact, to make it clear how I do this, I'm going to put a little switch here. So I've got all these circuit elements here. I've got lots of circuit elements, idealized circuit elements. I've got a wire that connects all these things. That's a perfect conductor. And there can be no potential difference across a perfect conductor. So between point A and point B here, there's no potential difference. It's connected by a wire. There's no electric field in the conductor, right? That's an ideal conductor. You can't sustain any electric field. That means the gradient of phi is 0, so phi is a constant from point A to point B. Okay, then I have a perfect resistor. And the potential drop across the resistor depends on how much current is flowing through it. Or another way you could say it is that the current flowing through it will depend on what is the potential drop across the resistor. Because the potential drop generates an electric field. Current flows in response to that. And the proportionality is the resistance of the resistor. And then I have so that's the voltage drop across the resistor. Then I have, if the capacitor is charged, I have another potential drop across the capacitor, which is proportional to the charge that's on the capacitor, and inversely proportional to the capacitance. Okay, and then I have a switch here, and I have a battery. These are all idealizations of real things. Wires have resistance, you know, real conductors except for superconductors, but like copper has some resistance. It's not a perfect conductor and so forth. All right, but we idealize these things. Okay, so the basic pieces here, in addition to the geometry, is the voltage on the battery, the resistance, and the capacitance in the circuit, and that switch. And now I'm going to close that switch. It starts off with no charge on the capacitor, and then I close it. So it starts off, the charge on the capacitor initially is 0. But when I close that switch now, I'm going to get current flowing through the resistor because there's a potential difference across it. And so I get current flowing. And the amount of current initially flowing is just the initial potential on the battery divided by the resistance. Okay, but we also know, remember that the charge on the capacitor, when that current flows, it starts charging the capacitor. As long as the current continues to flow, it's going to put charge on the capacitor plates. Okay, and now, in fact, the sum of the potential difference across the battery and the capacitance has got to be equal to the potential across the battery. This is Kirchoff's voltage law. I think I'm spelling Kirchoff correctly. There's 2 C's and 1 F or something like that. anyway, Kirchoff's voltage law. If I go around a loop, the sum of the potential differences has to come to 0 because the electrostatic potential is the same here. And if I go around, add up the differences all the way around, I got to come back to the same place. It's like this argument: if I'm in the Rockies and I take a hike and I come back to the same place and I sum up the uphill and downhill, it's got to come back to the same altitude. What goes up has to, if you're coming back to the same place, sum of ups and downs has to come out to be 0. So by Kirchoff's voltage law, I can write an equation that describes this this circuit. So this is called a circuit equation. It says that the voltage drops, the sum of the voltage drops across the resistor and capacitor have to add up to the voltage across the battery. And we've got this little bit of information here that the current flowing across the resistor is the derivative. Okay, so we have this plus the initial charge is 0, and we've got a differential equation to solve for Q of t. But before we do that, let's anticipate what's going to happen here. Going back to the diagram, initially there's no charge on the capacitor. Current is flowing through, but now it's charging the capacitor. And as the charge on the capacitor grows, so does the potential difference across it, which means that the potential difference across the resistor is dropping. Right? Because it has to sum up. The two have to sum up to the battery. So there's charge on the capacitor, then the potential drop across the capacitor is taking some of that potential drop. And so the current in the resistor is decreasing. And eventually, it builds up enough charge on there that accounts for all of the potential drop, and the current has gone to 0. So eventually, after a long time, how long we'll have to talk about here in a second, after a long time, the current goes to 0. And the charge on the capacitor now is taking up the entire potential difference. Oops, let's see. No, excuse me. It's times. See, there we go. Okay. So let's draw the what we expect to have happen here. The charge on the capacitor as a function of time. It starts off with no charge, and then it builds up, and we're going to find it goes asymptotically to V naught C. So now all the potential drop. It starts off, all the potential drop is across the resistor and none across the capacitor because there's no charge on it. But after a long enough time, the capacitor is fully charged and the current has gone to 0. There's no more current in the resistor. So it starts off V naught over R. It starts off and then decays to 0 like this, asymptotically approaching 0. And of course, these are related to each other by a derivative. Yeah, they're opposite. There, right. That's right. So I have a sign. I have to fix my sign thing, but they're related by a derivative. Okay. So in other words, the solution to that differential equation I wrote will look like this. That will be the charge. That's the solution to the differential equation with the initial condition that Q of 0 is equal to 0. And then Q at a very long time is equal to V naught C. This satisfies the differential equation, which you can demonstrate for yourself by direct substitution. Take that, plug it into the differential equation, and you'll get the solution to the differential equation. Okay, so that's the charging. I've charged up the capacitor plate then. So now I'm going to modify the circuit a little bit. Here we have the original circuit like this. We have a switch here, a resistor. we closed the switch, and that charged up the capacitor. Now let's open up the switch here. Now we have charge on this capacitor, which was equal to, the initial charge is equal to V naught C. This is the battery over here, charge now. That's what it charges up to. Now I'm going to construct the second path here, again with another, which is resistance. I'm going to have a different, for fun, I'm going to put in a different resistor, different strength resistor. God bless. Okay, so now I've closed the switch on the left to charge up the capacitor. Now I open it up, and the charge doesn't have any place to go. It can't go anywhere, so it just stays on the capacitor. So now I'm going to open switch 1 and close switch 2. Close switch 2. Okay, now what happens? The circuit on the left is open still, so nothing, it doesn't do anything. The circuit on the right is closed. The charge on the capacitor is going to go where?
Through the new resistor.
Through the second resistor, yeah. The current's going to flow now in this direction. And so the capacitor will neutralize itself by flowing the positive charge around the loop to the bottom plate. So it neutralizes itself. And eventually all the charge goes off the capacitor. So this is the discharge. So we charged it with circuit 1, now we're discharging with circuit 2. And the circuit equation is just as before, except that we don't have a battery in here. And this is the new resistor, R prime. Different resistor. Before we had the circuit equation had a battery, so there was a V naught on the left-hand side. Now there's no battery in the second circuit. And the initial condition here is that this plate was charged up by the battery originally, so that's how much charge is present on the capacitor initially when we closed the second circuit. Okay, and then we can solve this, and it equals e to the minus t over r prime c. This is the discharge, and this is just this exponential that goes to 0 like this. It's discharging back to 0, and the current, of course, is q dot. Yes, sir.
Is that 0 in the box, like the left-hand side?
Yeah, 0. This right here is 0?
Yes.
Yeah, it's 0. Why is it 0? Let's go back to the first example up here. Let's see. Here was my, where did my circuit equation go? Sorry. Where's my circuit equation go to? Oh, there it is. The circuit equation right here. Here in terms of the current, here in terms of the charge. So now we have just the capacitor and resistor but no battery. So the V naught is 0. But we still have the different resistor, and we still have the capacitor. So this is saying that the sum of voltage drops across the capacitor and resistor have to cancel each other out. Just all the way around the circuit, you've just got two elements there, the capacitor and the resistor, so they have to be opposite to each other, and they cancel out. So that's the discharge cycle. So you could go back and forth charging and discharging this resistor. And notice the expression here for the solution, right here. Notice that the time dependence looks like that. It's an exponential, e to the minus t over RC. That means that RC, if I've done everything correctly, RC has to have dimensionality of time. Resistance and capacitance, the product of resistance and capacitance has to be a time. And you can see that, remember the voltage, this was a voltage difference over the resistor. This is an electrostatic potential. And Q over C was also an electrostatic potential. Those things have to have the same dimensionality. So RC has to have dimensionality of Q over I, which gives it a dimensionality of time. Because the current is a charge per time. So that gives it a... Okay, so the time that it takes to charge and discharge is this product of RC, the resistance and the capacitance. And so I guess I didn't give our assistant enough time to set it up. Wednesday, I'm hoping to have in here an example of an RC circuit where we can watch the charging and discharging, do this experiment live in class, so you can watch it happen. Okay, so this is an application of electrostatics, and why it's included in here. It's just a kind of a brief introduction. There's still other kinds of interesting circuit elements. The next one we'll encounter is a magnetic effect, which is a magnetic inductor. And so we'll include a magnetic inductor in this circuit, and we'll see how it modifies the behavior of the circuits. And these are all passive circuit elements and also called linear circuit elements. Transistors and diodes are more complicated things and give different kind of behavior, but that difference given by transistors and diodes makes it possible to make really interesting circuits that do really interesting things. Okay, so anyway, this is the introduction to circuits for the time being. Okay, so you're going to do some homework on circuits for Wednesday. And so I wanted to give you an overview here in the last couple of minutes that I have in class. I want to give you an overview of what we did here in Chapter 1, in addition to the circuits. So remember, this is the electrostatic condition. And using the electrostatic condition approximately, so it's also called the electrostatic approximation. So the electrostatic condition is nobody move, charges stay put, don't rearrange themselves. Well, obviously you just saw them rearranging themselves in that circuit we did. So what we're doing in that case is applying the electrostatic condition approximately at every instant. So when that plate is charging, we say the electric field responds instantaneously. Change the electric field, the charge on the plate, then the electric field is given by the charge that's on the plate, and there's no delay time involved. The electric field changes instantly. So the electrostatic approximation is neglecting transit, the time it takes to transmit the electric field, changing the electric field through the planet. Okay, so no charges move is the full condition, and the electrostatic approximation is we can treat it as though it were the electrostatic condition, neglecting the transit time. Okay, so we find Maxwell's first equation. And there's two forms, the integral and the differential form. These are also called Gauss's law. Okay, so who can tell me those? Do you remember what those are? They have to do with the relationship between charge and the electric field generated by the charge.
The surface integral, or volumetric integral of the electric field dotted with the dA
Yes.
equals 4 pi q.
Yes. And that's the charge enclosed inside the volume. Okay? That's the integral form of Gauss's law, also called Maxwell's first equation. How about the differential form, which is related by the divergence, right? The divergence theorem connects these two forms.
Divergence of J is equal to the limit as delta V approaches 0 of the double integral sum.
Yeah, that's the definition of the divergence, which you're giving me there.
Oh.
So what I want to know is, though, I think that's what you're giving me. Yeah, because it's a limit. So that's the definition of the divergence. But now the divergence, this first one says that the electric field flux is proportional to the charge enclosed. So let's shrink that volume down to a point, dividing by the volume. So what do we get then? We get the divergence of the electric field is what? Proportional to the charge at that location, the charge density at that location. Those are the two forms of Maxwell's first law. They're equivalent to each other. They're just expressions related by the divergence theorem. So one is local because it deals with the electric field in the vicinity of a single point. The other one is integrating over an area. The first one we used to try to give us the electric field around various geometries using for a highly symmetric situation. You can determine the electric field, how it should depend on distance, for example. And we found the electric field for 3 different geometries. Actually, lots of geometries that are related to each other. Okay. Now we had some other relations. The force on a test charge is QE. Q times the electric field. So this is the force law. Yeah, that's kind of loud, isn't it? This is the force law. So it tells us, given the electric field, we put a test charge in there, what force will be present on the test charge, assuming that when we put that test charge in, that the other charges don't rearrange themselves, right? That's the assumption here, that we generate this electric field by bringing up some charges and putting them in place, and then we bring in a test charge, and we don't want those other charges to start moving around, so they can't be on a conductor, or we have to nail them down, glue them down, something to keep them from moving. Okay, so that's the force law. We also have this one, the divergence of the current. So this J is the current density and rho is the charge density, and they're related to each other. This is called the continuity equation. And it also expresses charge conservation. Why does it express charge conservation, do you think?
As the current flows out due to J, you're losing charge density within.
Exactly. Yeah, that's right. If you consider, remember the divergence, we would calculate the divergence by taking a small Gaussian surface around in the vicinity, small neighborhood of a point, and look at the flux going out of that Gaussian surface. Well, if current is flowing out, net current is flowing out from that volume through that surface, then it's got to be reducing the charges present inside. So we get that reduction that way. So those are related in that form. Current doesn't really come up very much because it's electrostatic, right? We're not supposed to have charges moving around, but if they move around, then there's got to be this relationship to the charge density. But since we're considering electrostatic case, J is supposed to be 0 here, which means that rho dot is 0. So if J is 0, that implies rho dot is 0. In other words, charges aren't moving around, right? So the electrostatic condition would be that J is 0, but we did encounter this continuity equation. Okay, and one more condition is present here, which we haven't spent much time talking about. Maxwell's, hang on. I think it's the third equation. No, it's the fourth equation. Who's got your book with you? I just had a Rick Perry moment. Yeah, hold on. Let me have, it's, yeah, thanks. You've read it, right? I mean, it's in the, I can look it up back here. Third. There you go. Thank you. Maxwell's third equation in the electrostatic form is that the curl of the electric field is 0. Okay, what does that mean? We haven't studied curl very much, but we did discuss it some. Remember, the divergence gives you the diverging of the field, and the curl gives you the circulation of the field. So the electric field doesn't circulate doesn't have vorticities, doesn't have vortices present in it in the electrostatic case. This is electrostatic, remember. Okay, and related to that is the fact that we can define electrostatic potential. It's very much related to this condition in the electrostatic condition. So we can define electrostatic potential. Remember, this is a lot like having a conservative force. In a conservative force, there's we can define a potential energy which depends only on position. In the electrostatic approximation, we can define electrostatic potential that's a potential energy per charge. And so we can work with phi or E. And phi is often easier to work with because when you're calculating phi from a charge, there's no directions associated with it, right? So if we have two different charges, Q1 and Q2, and I want to know what phi is here. At this location, I have these two distances, D1, D2. Phi, the total phi will be Q1 over D1 plus Q2 over D2. There's no vectors, no directions. It's a lot easier to calculate. Calculating E, I would have to have all these careful about the vectors and the directions and stuff like that. I can calculate phi and then take the negative gradient of it to get E. It's a lot easier to calculate things with phi. And that's what I was taught, that phi was a matter of convenience. But there is I think this book shows there's actually much more significance to the electrostatic potential physically. And that's one of the nice things about this book is it brings out the physical nature of phi and then something else we're going to encounter later called a vector potential. So when we get into magnetic effects. Yeah. Okay, so that's the empiriometric electrostatic theory in a nutshell. We've defined what we know about the electric field in terms of the charge density and what happens to any other charges put in place there as a result of the electric field that's present. So that's the nutshell of the empiriometric form. So that's the first step. Then we're going on later to let the charges move around. We're going to get currents and things like that. Okay, but this is the beginning.